All right, gang, here we go. This is for physics, Unit 9, Part 4.2. We're going to talk about resistance, alternating direct current, and that's about it for this video. All right. So, last video we talked about current. We talked about how electrons flow through wires and how we can kind of think about electrons flowing through waters as water flowing through a pipe. All right, and so you could imagine if the water is flowing through the pipe, and say your pipe is shaped, kind of like this, whatever, and then it gets to a portion here where it gets a little skinnier and then gets bigger again. Okay, you could imagine like your water is going to be traveling at a certain speed when it's over here, and then when it hits the skinny portion here, it's going to slow down, and then it's going to speed up again as it gets through. And you could say to yourself, well, this area right here has high resistance. Okay, and so really what we're talking about now is this idea of resistance in terms of electricity or electron flow. And so everything that electricity passes through has some given resistance, and this resistance is just how much does that object or does that material oppose the flow of charge. All right, so the formula to find that is simply the change in voltage over the current. Okay, you might also see this written as Ohm's law down here, V equals IR, super popular, very, very big. Okay, the SI units for resistance is the volts per amps, or volts per ampere, and then really it's just ohms, and it's got about the coolest symbol ever in my opinion. All right. Now, Ohm's law is a pretty interesting idea because you get this idea of certain things obey Ohm's law very well and other things do not. And you can kind of look at that, reading about this is pretty interesting because there are certain materials that as you change the voltage, the resistance will actually change quite a bit. Other things, though, are very pretty much stable. Their resistance stays pretty much consistent. And so what you end up with, if it's what's called an ohmic material, then as you graph it, you end up with a straight line where that the slope of that line is your resistance of voltage versus current. All right. But anyway. Okay, so let's do a practice problem using this formula. Okay, it says how much charge flows through the bulb, or sorry, a typical 100-watt light bulb has a current of 0.83 amps. How much charge flows through the bulb in 1 hour? So this is using our current formula. Okay, remember current. Okay, current is equal to charge per time. Okay, or not C. What am I doing? Charge per time, and it says it wants to know how much charge, so we'd rearrange that so our Q value is equal to I times our T. All right, so our current is 0.83 amps, and our time here, remember amps have to, our SI unit is in seconds, so we'd convert that to seconds, so that'd be 3600 seconds. All right, so 0.83 times 3600 times 3600. And we get how many sig figs do we want? 2 sig figs, so we get 3.0 times 10 to the third. And this is charge. Charge starts with a C, so does coulombs. And then it says how many electrons would flow through this in the same time period. Well, the easiest way, so that's the first answer. The easiest, there's two ways to go about this. We could convert amps to electrons and then multiply it by time. Or we could convert charge to electrons. And so really we could go either way. Let's go ahead and just convert charge to electrons. So we got coulombs and we're going to electrons. Remember the charge on one electron is 1.602 times 10 to the minus 19th coulombs. So we just take our answer here divided by 1.602 e to the negative 19th, and we get 1.9. Let's see, I can't remember. Did I move my face for this video? I did. Oh no. Oh no, I grabbed the wrong thing. All right, and so we get this guy, so we get 1.9 times 10 to the 22nd, and this would be electrons. All right, look, we got the right answers. Hallelujah. And it says this same bulb is connected to a 120 volt potential difference. Find the resistance of the bulb. Well, R, we just learned that formula right here. Okay, R equals delta V over I. Okay. So R is equal to change in voltage over I. All right, and so you get 120 volts divided by our current. It's the same current, so it would be our 0.83 amps. So all we have to do is take 120 divided by 0.83, and we get 144.5. How many sig figs? Just 2 sig figs still. So it would be 140. And the units for resistance is ohms. All right, or 1.4 times 10 squared. Same diff. Same difference. So factors that affect resistance, these are the 4 that I want to focus on. All right. Length affects resistance, and then this kind of makes sense if you just think about it in terms of that wire or water traveling through a pipe. The longer that skinny section is, the more resistance it's going to have, right? That makes sense. So the longer your wire is, the more resistance. All right. The cross-sectional area, now this one's slightly pretty, or kind of the same idea as your water pipe, right? The bigger around your pipe is, the easier it is for your water to travel through. Same kind of idea for our electrons, or our charges. The bigger around, or the bigger gauge that wire is, the easier it is for our electrons to travel. And that essentially what that means, remember before when we talked about electron drift, right? We had this electron traveling from one point to the next. The bigger this pipe is for it to travel in, or this wire, the more room these electrons kind of have to fit around each other, and the more possibility there is for this electron to pass through, or be able to pass it through in a way that's going to go from one point to the next. All right, material plays a huge portion in its resistivity. It's probably the #1 way to control resistivity. Stuff that's really good conductor, like copper, has a very low resistivity. Iron does not have as good of conductivity. It's still a fairly good conductor, all things considered, because it's a metal. However, it's not nearly as good as copper is. All right. Now the crazy one here that I think is a little counterintuitive is temperature. All right. The metals actually conduct electricity better at colder temperatures. That's why when we have like superconductors and stuff, they always have to be equipped with like liquid nitrogen, liquid oxygen, stuff like that. So lower temperatures actually lower resistivity. And the way I think about this, at least remember it, is that the more energy something has, the higher temperature it is, right? And so you think, oh, the electrons have more energy, so they move more. But that's not quite right, because the electrons are going to move regardless, because they're so dang small and high energy anyway. The things that are going to be moving more as you raise your temperature are really the nucleuses of these atoms that are making up your wire. So these little guys in there, at a low temperature, they're going to be vibrating, but just a little bit. As you increase the temperature, they're going to be vibrating more and quicker at a higher frequency. And so because they're vibrating more and at a higher frequency, there's a higher likelihood of them getting in the way of those electrons traveling through that wire. So it increases the resistance. All right, so that's kind of how I think about it. So high temperature is high resistance. Low temperature, low resistance. All right, lots and lots and lots of different applications to resistors. We use resistors all the time in just about everything that uses electricity. And one big reason that we do is because it stops a short circuit. And we'll talk about what short circuits mean here in a couple videos, I think. All right, but we use these resistors in order to control the current to different components we're talking about. If you don't want all 120 volts of the energy coming into your house to go straight into the light bulb you just turned on. That would burn out the light bulb right quick. All right, so we use resistors to slow down that current before it gets there. All right, we also have variable resistors. Variable resistors are called potentiometers. Okay, pretty fancy name, but essentially there's something that's going to change that potential energy. All right, potentiometers. All right, and they're used a couple applications, dimmer switches and volume control. So if you have like some, like a little dimmer slider or something like that in your house, essentially what that's doing is it's using a potentiometer to change the resistance of the whatever the wire is passing through before it goes to the light. And so when it's really dim, when you have it on the dim side, you've got really, really high resistance, and at the low side, you've got really low resistance. Or at the low side, when you're really, really bright, you have low resistance. All right. Human bodies, this is kind of interesting. Human bodies resistant ranges from 500,000 ohms, so this is if you're like completely bone dry, to about 100 ohms, which is actually pretty low. And that's when you're soaked with salt water. So for whatever reason, you've decided to jump in a bunch of salt water. All right, maybe you're swimming in the ocean or something. So really what this essentially means is that the human body is fairly decent at conducting electricity, especially if you're sopping wet. All right. So currents, like just a couple of ideas for currents and so on and so forth. Resistant or currents about this value here cause a tingling sensation. So when you lick a 9 volt, it's somewhere around here, probably around like 0.02 or something like that. And then currents greater than 0.15 amps can actually disrupt your heart's electrical activity, which is not a great thing, because so your heart, you've got essentially your heart is shaped something like this, right? And you've got different portions of your heart and 4 chambers, right? And in order to pump blood from one chamber to the next, essentially what it does is it sends electric signals to the muscles in the different parts that push the blood through, open up the valves that are, and so on and so forth. But it's sending these electric signals. So when your body gets shocked by a bad enough shock, then it actually will interrupt the signals, or your muscles will get more than one signal at a time, or 2 opposing signals, and then that's where your heart attack starts happening, is because they actually go into what's called arrhythmia, where your heart gets out of sync. All right, it's no good. Bad news. All right, we got to talk about a couple different types of current. You might have probably heard about these before. You got direct current. Okay, these a big application of these are starting to, direct current is starting to take over the world a little bit, okay, especially as technology kind of advances a little more. It's got some advantages. I'm not an expert in this stuff by any means, but it is super interesting. Direct current, if you're interested in American history and kind of the Industrial Revolution and so on and so forth, research what occurred, kind of like the power wars. I think that is how it's kind of an interesting way to think about it, is between Tesla, who was a proponent of direct current, and Edison, who is a proponent of alternating current. And we'll talk about both of those just very briefly right now. Okay, so the first applications, or the first real instances of direct current, is using batteries to produce electrical energy, and so that's using the chemical energy to make electrons flow from one place to the other, and really causing this electron flow. And so this causes direct current. Okay, so it's called direct current because essentially it's not a very interesting name, but because the electrons only flow in one direction. So we can see that we've got this current and time, and they're just kind of going just there to the right. All right. Alternating currents, though, are slightly more interesting. They alternate from positive to negative. So essentially what this means is that these electrons are vibrating back and forth as they go. They're not just going in one direction like they are in a direct current. They're vibrating back and forth. And this is caused by mechanical energy. All right, mechanical energy, so either like a turbine or the car engine in your car, or like falling water moving a windmill, or the thing. Shoot, dang, water falling through. Anyway, so it turns that thing, water wheels, okay, and so they'd use in the old school days in order to grind up their wheat into flour, so on and so forth. All right, so we turn this mechanical energy into electrical energy, and it goes back and forth, and this is caused and so essentially what this means is that this electric signal is vibrating back and forth, and this can actually be a lot more dangerous to us because it kind of sends this signal that goes in your body, and that's really can mess with your heart. All right, because with a direct current, it kind of sends one time. If it didn't mess with it, then you're probably safe. But alternating current, because it kind of keeps going back and forth 60 times per second, it can be pretty nasty. All right. It says here alternating current is better for transferring electrical energy to your home. Now this is kind of a little true and then a little not true. Alternating current is actually what it is it's in order to transfer energy over long distances, it's best to do it at high voltages. But however, it's really hard to successfully utilize as high voltage. Also, it's pretty dangerous. So the power lines that bring your power from the power plant to wherever you're living, wherever you are, is through the lines. It's traveling at many thousands of volts. However, the transformers that are right outside your house, or maybe outside your neighborhood, depending on how it's set up, will do what's called stepping down that voltage as it comes across. So through the wire just outside, it's many thousands of volts, but then it steps it down to either 240 or 120. as it gets closer to your house. And so high voltages are better to transfer it. Now, the reason alternating current is better is not because it's more efficient or it doesn't lose it, but it's actually, at least based on current technologies, it's actually a lot cheaper to do the stepping down. And that's the reason they say alternating current is better. Direct current is actually, like, in most respects better, but alternating current is cheaper, so that's kind of what we go with for now. All right. Last little thing here. And it says we're just looking at this energy transfer. So we've got this complete circuit here. We've got our battery, and remember we got a potential difference between the positive and negative terminals here. And we're going across this alligator clip, across this wire, through a light bulb, and then out the other side back to the battery, completing the circuit. And we want to keep track of, well, what happens to the electrical potential energy as we travel between these different letters, A to B, B to C, C to D, and then back from D to A. All right, and we want to kind of come up with our answers here. So let's just walk through here. When our electrons are here at A, they're going to be at a high potential energy. Okay, we're going to have very high potential energy. As we travel across this wire, though, this wire has essentially zero resistance. And so because it has zero resistance, we don't really lose any energy. So that potential energy is going to remain constant as we go from A to B. When we go from B to C, we're going to lose our potential energy because this thing has a very high resistance. And remember, we talked about this a couple videos ago. We've got a light bulb, right? Here's our light bulb, and then here's our filament, right? And here, this filament is essentially just something that has really, really high resistance. And as we send electricity through it, our electrons slow down, and they undergo what's called, and heats up this metal, and it undergoes black body radiation, which essentially means it just glows on its own. All right. Then from C to D, again, we're traveling through a wire, very low resistance, so our potential energy doesn't change. And then from D to A again, we're going through the battery, and then we're going to end up with high potential again. All right. And so that's it for this video. Not too bad stuff. Talked about resistance, talked about alternating and direct current, all right, and talked about and did some practice problems. So that was fun. Next video, we'll talk about power and wrap up kind of our talk of those three main points. All right, so do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.